And the plenary session will be led by Mr. Joko Utomo. Ladies and gentlemen, please welcome Mr. Joko Utomo. Okay.
Okay, thank you very much for Master of Ceremony for this time. Good afternoon, ladies and gentlemen. Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, welcome to the last sessions of this conference. I'm Joko Utomo to be moderator for these sessions, and for this session we have two keynote speakers actually. The first one is Associate Professor Dr. Ahmad Taufiq, and the second one we have Dr. Jason Scott from USA. But for the first session, we have Associate Professor Dr. Ahmad Taufiq. I would like to read the brief descriptions about Associate Professor Dr. Ahmad Taufiq. He graduated from undergraduate program in University of Malang, and then he got a master degree and doctoral program in 10 November Institute of Technology, and he currently works on magnetic materials. And actually, he is also one of the best lecturers who has the highest publication in this university. Please give applause to Mr. Taufiq. Okay, without further ado, please welcome to Associate Professor Dr. Ahmad Taufiq. The time is yours.
Okay, Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Okay, now we are going to next sessions. I would like to deliver the talks entitled "Exploring Natural Iron Sun to Produce AMS, Ferrite Oxides, Magnetic Fluid for Antibacterial Application." Based on the title of the conference, Electromagnetism, Rock Magnetism, I think Prof. An and Prof. Satria Jaksana have already discussed. Now we are going to magnetic material, especially for nanomaterial. Some of what also was already discussed with Prof. An. So, this is our team. This is my best friend, soulmate, and this is from Singleton Wright Research Institutes, and from ITS, and also from Tokyo University, and from Riken Design Center. So we have already mixed the research for about 13 years. Next. Okay. Natural iron sand in Indonesia. This, for example, this is not big mountain, but iron sand mountain. This is also sand from the beach from East Java, Indonesia, and this is business of iron sand. And this is researcher. So we have big opportunity, and also we have big problem from iron sand Indonesia based on the data. We know that we look at in here, for example, nickel, gold, and we are focusing on iron sand. We call it by Pasir Besi Indonesia. By year to the year, this is the current data for mining Indonesia. Now, the latest data, this is about 2 million ton. The latest data from Indonesian government. So usually the iron sand Indonesia is made for the building, and this is very cheap. And several years ago, the iron sands was exported to other country, but now very strict. Our government makes new regulation. Therefore, as a researcher in university, especially in Indonesia, we have big challenge how to utilize the iron sand in Indonesia to be or to enhance the quality, both scientific or economics aspect. Therefore, in our team, in our research group, we explore the iron sands to produce some nanoparticle, for example, like nanopowder and ferrogel, and also we produce magnetic fluid with some method like co-precipitation, ultrasonic, and combination of electrospinning and co-precipitation and ultrasonic to produce high purity of magnetic nanoparticle. We know that the price of nanoparticle based on ferrite nanoparticle is very expensive, but in our laboratory we can produce with a simple method and fast method using natural iron sand. So at least for 10 years we develop several methods to synthesize this method, and we have already more than 10 patents granted about nanoparticle from iron sand. Okay, to increase the performance application, especially for antibacterial, for drug delivery, or for sensor that we have already done in our university, we make some dopings based on magnetic Fa, we call it by Fa3O4, by some other elemental for metal transition, something like mangan, Mn, like zinc, Zn, and cobalt, and the other elementals for metal iron. So our target in here, we can how to produce the magnetic nanoparticle, but for nanopowder, or ferrogel and ferrofluid in high purity. This is our challenge, because the iron sand, we know that the iron sands has many impurities like titanium and the other elemental impurity. And because we are in here is about the physics, so we investigate the hierarchical structure, especially for ferrofluid. For powder or bulk material for nanoparticle, it is very easy to investigate, to study the hierarchical structure. We can measure, we can characterize using transmission electron microscopy, scanning electron microscopy, or atomic force microscopy. But the problem is, for the magnetic fluid or ferrofluid, we have difficulty because we should prepare the sample in situ preparation. If we make the ferrofluid dry, so the fundamental character like hierarchical structure is not real character. So we need advanced characterization using synchrotron or using neutron that we have already done in Japan and the Batan in Indonesia. And the last ones, we also develop the potential application. Now we develop for magnetic and temperature sensor, and also for hyperthermia for gel with Dr. Sunaryono. And now we just focus for antibacterial or antifungal application. Okay, the synthesis that we developed in our laboratory, this iron sand, we know that the iron sand has many impurities, so we extract the iron sands, especially for the black iron sand. We know that the black one is consisted of mines compound magnetite, not hematite or not Fa2O3 or not FeO, but content of Fe3O4. We call it by magnetite or black iron oxide. So we spread with physical treatment many times using permanent magnet, and we can get the powder of iron sand that's almost 100% consisted of magnetics, but the particle size is still in micro size. And using this method, the first one, the iron one was dissolved with HCl at the acid base to makes the solution ferrite FeCl2 and FeCl3. So Fa3O4, if we mix reaction with the HCl, it will produce two solution consisted of FeCl3 and FeCl2, and also the water. And then because the remains product something like salt, so we continue by next step the process using an H4OH to take the chloride and the other impurities, so we can produce the nanopowder in here, Fe3O4. This is the simple schematic. For the first reaction only 15 minutes and the second reaction only about 20 minutes. So in 1 hour we can produce a nanoparticle, theoretically. But in reality, we should control another and many aspects. But my student last year, she already successfully synthesized only 2 hours. And here, this is schematic. And the first one, dissolving agent, and the second one is precipitating agent. Okay? The next section, if we would like to produce the magnetic fluid, something like this, if we mix the nanoparticle in big particle size, this is very impossible to produce magnetic fluid. So we should make the magnetic nanoparticle, ferric nanoparticle, and very small size with high homogeneity and with high impurity. So we can disperse in water, in alcohol, on other liquid carrier to produce the magnetics in liquid phase, something like this. So we need something like surfactant. If we have already produced the magnetic nanoparticle, the next step to produce magnetic fluid is cover the surface of magnetic particle to prevent agglomeration. We know that theoretically in physics, if the particle very small, and because van der Waals force, the interparticle between one particle to other particle has a strong attraction, so it will make or it will produce aggregation. For aggregation, it is very difficult to produce high stability ferrofluid. So we need surfactant agent. We have developed two methods. The first one, single method by single layer, and 2 years ago we have already successfully produced double layer surfactation. So the high stability of ferrofluid can be obtained easily. And this is schematic. We know that the circle in the center here, this is magnetic nanoparticle, and here the yellow one is the first layer, and the blue one here is second layer is double surfactation. So it is give us the guarantee that the ferrofluid in magnetic nanoparticle will be stable for a long time. This is our product in here. Okay. Next, for antibacterial or antifungal system, we just makes collaboration with Department of Biology, our colleague, and also with medical faculty in other university. Okay, this is our characterization and development of the application. We already synthesize and characterize in hierarchical structure using X-ray diffraction, using infrared Fourier transfer, infrared spectroscopy, using TEM, using SEM, and using other machine. And also we have already investigated the magnetic property using VSM and sweep magnetometer, both ohms magnetization and also FCCFC to ensure that this is our product, our sample form in superparamagnetic. Okay, this is the sample one. We have produced the magnetic with some doping, zinc, cobalt, Mn, and chromium. We can see that because of the different ionic radii of elemental substitution in here, we can see in here there are no other peak. So it means this is single phase, or we can see only one phase crystal structure in here, that is spinel structure. This is our model in here, and theoretically makes some doping or substitution by other element, something like Mn, zinc, or other element replacing the Fe2 plus or Fe3 plus will change the lattice parameter because the different ionic radii. And the second one, the big effect after changing the lattice parameter and crystal volume and also the crystal structure, because the different spin magnetic of the Fe2 plus or 3 plus with the other element, for example like mangan, so the magnetic character, especially for saturation magnetization, will change significantly. And the second one, this is the magnetites doped by mangan from 0 until 1 in molar ratio. We can see in here the higher the mangan composition, the lower intensity, and also we can see in here there is the shifting peak from the right position in the higher to theta to the lower position. It means that the doping process or substitution process of Mn replacing iron has been successfully injected in here. So where is the Mn or iron in here? We can make theoretical formulation using chemical equation in here that we can guarantee mangan in here replaced in the tetrahedral position, because we know that in the spinel structure is a cubic structure. We know that ABC lattice parameter is same, and also the angle between XYZ is 90 degree. So we can see in here in the system of spinel structure there are two subsystems. The first one is tetrahedral side and the second one is octahedral side. So the mangan ion in here replace the Fa ion in the tetrahedral position. The second one, this is the good one. Lies Indonesian version. Next is Swiss version. Okay. The second one, because Mn mangan has the higher magnetic moment for 5 spin and Fa is 4 spin, so theoretically the magnetization will increase about 25% only by replacing one atom from Fe by Mn. So it will make the application of magnetite will increase significantly. This is lattice parameter. The higher the Mn composition, the higher lattice parameter, because we know that the ionic radius of Mn is 0.89 angstrom, larger than Fa2 plus and Fe3 plus. Okay. The next is, what about we change the Fe2 plus and 3 plus with zinc? After Mn, we make modification with zinc. we know in here, the higher the data in here, the higher the composition of zinc. We know also in here, zinc also has ionic radii larger than Fa3+. So the position, peak position, move to the left position or to lower angle of the theta in here. Based on the FTIR characterization in here, zinc and also mangan in here, metal oxide were detected about the lower wave number in here. And we also combine, this is for powder, using TEM. Particle size was about 10 up to 12 nanometer. This is very, very small. Theoretically, about below 20 nanometer, we can say by some books, magnetic book, we call it by super paramagnetic material. But we should calculate, we should investigate using magnetization characterization. Crystallize, the higher the zinc composition in the system, the lower the crystallized size, because more complex structure and the nucleation process of the magnetic nanoparticle more slower. So the system have more time to make or to produce magnetic with lower nanoparticle size. The next, we also make a template to make a guarantee that our sample, our nanoparticle is made in nanometric size, in a stable size. In here, we make template here by diethylamine. This is a chemical process in here. The addition of template in here doesn't change the crystal structure. However, if we check in here, the intensity and broadening peak change. Therefore, crystalline size also reduce by increasing the template composition. So it means the template, diethylamine play as an essential key, as essential role in reducing the particle size of magnetic. And we also investigate using infrared spectra the magnetic system in tetrahedral or tetrahedral position were successfully detected in here. This is also these data were published last year in Journal of Magnetic. And the next data, this is the interesting data. We also mix some doping with cobalt. The higher the cobalt doping also makes the particle size higher because the difference ionic radii. But the problem is, if we mix some doping with the highest composition, there are some peak too in here that it will produce the other compound. We call it Fa2O3, mahimid. For hierarchical structure, we characterize this sample using synchrotron small angle scattering. The data something like this. If we see this data, this is quite similar. But if we feed some data using high precision method, using mathematical approach, we can obtain the hierarchical structure that we know that magnetic nanoparticle, especially in ferrogel and in ferrofluid, in magnetic fluid, consisted of the building block, something like this wall. So the building block makes the second, the bigger cluster to make something like this. So when ferrofluid covered by PEG, like polymer, this is magnetic fluid, the primary particle, and this is the polymer, and the composite, something like this. The data we make a simulation like chain for the ferrofluid and make particle cluster, the bigger one, something like this, and in here covered by surfactant. if we measure using TEM or the other technique, this is very impossible to obtain this data. Okay, the hierarchical structure. If you are from physics, theoretical physics, please see this one. If you are from geophysics, please see this one. If you are not from physics and geophysics, please see this one. Okay, we can see in here, this is the raw data from small angle neutron scattering. We have the data in here. This is Q, is momentum transfer, the incident beam of the nuclear energy, and reflected beam in here. So this is the intensity of the nuclear. If we fit using this mathematical model, we need 3 mathematical model. The first one is, we call it by form factor, and the second one is structure factor. Form factor something like this. If this in this room consisted of many students, for example like this, or many lecturer, this is a primary particle, and how the primary particle construct row something like this. This is we call it by the structure. So this is primary. This is a structure factor. So mathematical model, we should combine the model from form factor like as a primary particle and the structure factor at the bigger building of the system nanoparticle by this one. So we have form factor and structure factor, and we need fractal in here to combine the form factor and the structure factor. So we make a simulation something like this. This is magnetic particle. This is for a magnetic fluid. Okay, next. This is also data. This data was accepted 1 week ago. And 1 week ago, I got an email that is accepted after 2 years, more than 2 years. So if master student, you have time for 2 years, you will be longer. Okay, this is using a neutron. The electron beam, this is about 40 meter. We have two. So the machine, the tunnel to inject the neutron about 100 meter. One data, we can take one data 1 week. If we have 5 data, it will be more than one month if normal condition. However, usually the reactor will shut down every two days. This is so the data will be taken about 3 months only for taking the data, not for analysis. Analysis, Dr. Yono, more than 1 year. But this is the challenge for the student especially. This is the data. We have a good interesting data in here. This is the powder. This is ferrofluid, magnetic fluid. We know that if the powder, because this is a super paramagnetic material, the spin orientation is randomly oriented without external magnetic field. The spin orientation is random. So without external magnetic field, magnetization will be 0 in here. Because the nanopowder, the particle will be agglomerates. We mix a model something like this, and when we applied external magnetic field up to 1 Tesla, the scattering something like this, quite similar. What is the meaning of this data? From this data, after analyzing, we can see that the presence of external magnetic field just only move particle or spin. Where is student? You are not student. Will move spin, but the particle not. For example, like this. This is the particle nanomagnetic. This particle, your heart is spin, for example. So the neutron only move spin, not your body. So the orientation is something like this. The structure is same, but the spin lines following the external magnetic field. However, if we applied external magnetic field for the ferrofluid system, we know that the ferrofluid is something like this. And when we applied some external magnetic field up to 1 Tesla, this is an isotropic scattering. From circle become anisotropic. What is the meaning of this data? Despite the spin orientation, the particle also oriented following the spin orientation. Why the magnetic particle in ferrofluid also oriented following the external magnetic field? We know that in the ferrofluid, the particle is easily moved because the magnetic nanoparticle disperse in liquid carrier. This is the new phenomena in magnetic fluid. This is spherical section of nanoparticle. This is Dr. Sunaryono. When he was still young, several years ago. It also published in Springer this year. Yeah. This is ferrogel. Ferrogel, we make more simulation, computational method. We produce the particle something like this. And last night, our paper also accepted. My master student, she has 3 paper. She just graduated. So last night, this is accepted. Good luck for you, my student, Juanita. Big applause. This is the combination from hydroexcivated magnetate from natural sun. Okay, next, maybe, sorry, you can click. This is our product, magnetic and gel. Click. Okay. What is the remaining time?
1 more time. 8 minutes.
Okay. It has also granted for patent. Please give applause for Dr. Sunaryono. This is magnetic ferrogel. This is not magic, but physics. Yeah, move. Yeah. T, Taufiq. Yeah. Okay, T, the last one. Yeah.
S.
S, Sunaryono. Soulmate researcher. Okay, next presentation. Eight minutes. Okay. 8 minutes, 20 slide. One slide, it means about 30 seconds. Okay. No. Okay. The next one in here, the hierarchical structure of nanopowder. We make combination of some mathematical model. This is high resolution TEM. The data from neutron, something like this, and for high resolution TEM, something like this. Quite similar, because this is a nanopowder. Nanopowder can be measured, can be investigated using TEM and neutron. Is also published in Springer. And magnetic properties. We measure it in the University of Tokyo. From this data, we can see in here, there is no coercivity. This is give us the guarantee that this is super paramagnetic. From the particle size, not fully give us the guarantee that this is super paramagnetic. From this data, this is super paramagnetic, no hysteresis. From very magnetic change to super paramagnetic. But we also investigate using CFC and FC. We know that below room temperature, this is the blocking temperature. The blocking temperature is concentration, the block of the spin. This data also give guarantee that this is super paramagnetic. This is for the fluid. The back data, this is for the powder. What is the difference between powder and ferrofluid? The data is quite similar, but magnetization is lower because the particle size is lower than nanopowder and cluster. There are several effects, but we focus in here. In ferrofluid, in magnetic fluid, there are two data in here: freezing temperature and blocking temperature. In the powder on back sample, we just have only one data, blocking temperature. But the ferrofluid we have freezing temperature. This data originated from the liquid carrier and surfactant. So the freezing of the liquid carrier and surfactant. If we take zoom out the data, will be something like this. This data also published in Nano. Antibacterial application. This is antibacterial application. What is the difference between biological drugs treatment for antibacterial and magnetic nanoparticle? There are basic difference, the fundamental difference between drugs in biological and nanoparticle. We know that in nanomagnetic, despite the small particle size will produce the increasing ratio of area to the volume, it also has electromagnetic. Plus, the charge will be plus and minus in here. So, the phenomena, the magnetic nanoparticle covered by surfactant will be plus, and bacteria minus. We know that the basic fundamental physics in senior high school or junior high school, if we have charge plus and minus, it will be attracted each other. So, the magnetic nanoparticle will be easily attract the bacteria, so it will kill better or easily than conventional drug. This is the new phenomena of the magnetic nanoparticle. And the second one is still under review in Xavier solid state. It was submitted 1 month ago. We propose something like this. If we zinc doped by magnetic, the data will be like this because the cover of magnetic, the Fe2 plus and 3 plus and Zn, this will be minus of OH. So bacteria cell will attract and also will kill easily by external magnetic field. Despite we give magnetic nanoparticle, we also make external treatment by using external magnetic field. Based on the data, it also can kill the bacteria more significantly than conventional one. And the last one, for antifungal. Despite for antibacterial, we also make a treatment for antifungal application. We know in here, we use Candida albicans. The smaller particle size tend to be easier for magnetic to enter the wall cell. So it will kill, initiate the dead cell also easily. Now, we still in current project, maybe it will be submitted for at the end of this year. We also make drug delivery using doxorubicin. This is our schematic. and this is our first data in here, that magnetic nanoparticle in ferrofluid has good performance for release of doxorubicin as drugs anti-cancer. This is also the current project. Conclusion: the Indonesian natural iron sand has been explored to produce magnetic nanoparticle both in powder, in ferrofluid, and ferrogel, and they exhibit single phase, high purity, super paramagnetic, and also the ferrofluid and nanopowder exhibit as excellent agent as antibacterial and antifungal agent. Thank you.
Okay, thank you very much for your interesting and informative talk for Association Dr. Ahmad Taufiq. Now we open the sessions of question and answer. Is there any questions for the audience? Okay, is there any questions? Okay.
First of all, I would like to congratulate you on your good work. It's very good to see this kind of progress. I have a simple thing, because probably I could not really catch up with you. How you produce the like a nano-size particle from the micro-size iron sand? Do you have like a physical process or chemical process to produce the nano-size particle?
Okay, thank you very much, Professor Satria Bijaksana. In 2009, my Dr. Surayono with me, about 2 or 3 years, synthesized the magnetic nanoparticle used by using physical process. We make by grinding and also by what is that, Dr. Surayono? Ball milling, and the last one we use high energy milling. But we know that the physical method, physical technique, very difficult to produce magnetic nanoparticle in very small and in high humidity. So after 3 years, we couldn't get the nanoparticle, so we moved to the chemical process. The first one by co-precipitation. We know that Fa3O4, this is from iron sand. Fe3O4, we spirit by chemical reaction using HCl. If Fa3O4 plus HCl, it will be FeCl2 plus FeCl3, another salt, and also water. After FeCl2 and FeCl3 obtained, so we take the Fa2 plus and 3 plus using base, for example like NHOH, natrium hydroxide, for example like this. So FeCl2 and FeCl3 will be taken by base, so it will produce Fa3O4 and other impurities. Impurities will be easily moved by some treatment using water treatment. So we can take by using magnetic permanent external magnetic. And the second one, this is more powerful than co-precipitation. We also produce magnetic nanoparticle using chemical, physical and chemical combination, co-precipitation, and also using ultrasonic treatment. So when we have already produced the FeCl2 and FeCl3, so we combine, we make co-precipitation in some reaction, and also we inject the make treatment using ultrasonic with high frequency. So the larger particle will easily move. So we can take the magnetic nanoparticle in homogeneous particle. And the last one, we also try using electrospinning. But the problem is if we synthesize magnetic nanoparticle using electrospinning, the data will be something like fiber. So it is difficult to make ferrofluid. But to make something like tissue, this is very powerful. For example, for anti-radar application, my master student now also doing this work for anti-radar application. This is powerful. But for ferrofluid, our ferrogel also this is very powerful for hyperthermia and also antibacterial and drug delivery. So chemical, it means that chemical process, chemical treatment is more powerful than physical treatment. Thank you.
Okay, any more questions? Okay, if we don't have a question, actually I have a question for Dr. Ahmad Taufiq. Actually, the superparamagnetic material has many applications. So if we just have ferromagnetic material, is it possible when we change from ferromagnetic material to be superparamagnetic material, just adjustment like a method or doping another material? Is it possible, doctor? Is it possible that we want to change from ferromagnetic material to be superparamagnetic materials?
Okay, very good question. This is a basic concept. We know in magnetism, there are some character of the magnetic material: ferromagnetic, paramagnetic, diamagnetic, then antiferro, and then ferri. Yeah. So when the ferrimagnetic, actually the ferrite nanoparticle in our system, actually in the Bach system, this character is ferrimagnetic. We know that in ferrimagnetic, the spin up and down is not similar. So we have remind data. For antiferromagnetic, we have spin up and down is similar. So a cancellation. If superparamagnetic, because the quantum effect, Dr. Reni can explain. Because the particle size, we can, the ratio of the surface and volume, it will be the quantum effect. So from the ferrimagnetic will be moved to the superparamagnetic. Actually, like Professor An's presentation, he showed good data. The first one is something hysteresis, but we have not very thin. Like your presentation, and the second one for the superparamagnetic, very thin, no hysteresis. So the data will back to the initial position. You can join my course for S1 magnetic every Wednesday.
Okay, any more questions? Okay, if there is no question, I would like to conclude this presentation. Iron sand has many impurities, but we can change to the better one. We just we give adjustments such as method and then the doping of another materials, and the utilizations of iron sand for some applications such as delivery drug and then biomedicine and antibacterial. Okay, this presentation, and thank you very much again for your interactive and your informative talk. And hopefully this presentation will be beneficial for all of us. And thank you very much for your audience, and the time and place I will give back to the master of ceremony. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Mr. Joko. Now we are about to have another coffee break.